With ChatGPT, you type in text and get responses back in text, but it's also possible to speak to ChatGPT and get responses back in speech. The underlying technology is called GPT-4o, where O stands for Omni, meaning all forms of input and output. This allows not just for text assistance, but visual assistance and voice assistance. Now, OpenAI's models are private, so we don't know exactly how GPT-4o is built. But HuggingFace have now made available an open source implementation of a voice assistant or speech-to-speech model. In this video, I'll explain how to run the speech-to-speech model on your Mac or on a remote rented GPU. I'll also cover some tips to get high quality and fast responses. And so for agenda, I'm going to start by describing at a high level how these multi-input or speech combined with text models work, also called multimodal models. I'll talk about the modular approach that Hugging Face takes versus the more integrated approach that's used in the Llama 3 model, and also most likely some variant of that by OpenAI. I'll comment then with a few remarks on the modules you can use, so you can choose which individual modules or models to include within the Hugging Face model. So I'll talk a little bit about making the right choices there. Then I'll show you a demo of running start to end on a Mac. So you can actually run this locally on a Mac M1, M2, or M3. It's going to be challenging if you're trying to run on Windows or on a Mac that's with an Intel chip because the inference will just be too slow. However, if you don't have a Mac or if you don't have one of those Macs, you can run on a rental GPU. And I'll show you how to do that on a service like RunPod or VastAI. It's a one-click template setup that then requires you to connect with your laptop to the remote server. It's pretty straightforward, and I'll walk through all those steps. And last of all, I'll talk a little bit about how you might improve latency. That's the speed of responses, which is critical for voice. And I'll talk specifically about using UDP versus TCP ports in order to improve latency. It helps to get started thinking about these omni or multimodal models just by thinking about a text-to-text model like Llama or GPT-3 or GPT-4, the original text-only models. So here you have tokens or words that are inputs, so the quick brown, and these would go into the transformer, which has got multiple layers, and the output here will be the next token. So it's a next token prediction machine that is predicting the next word here. In this case, it's fox. Tokens in and tokens out. Now, when we move to speech, what we want is a model where we have a wave of my voice. So this could be my voice saying something. It's just a sound wave. And we have the first chunk of the wave, a second chunk, and a third chunk. And what we want to predict here is the next chunk of the wave, which would be some output here. So you can see a little bit this analogy of what it would look like if we did a speech-to-speech only model. And we wouldn't have tokens here that are words. We would have to come up with a way to represent these snippets of voice as vectors. So this is a speech-to-speech model. Now, if you want to build a speech-to-speech model, probably you have already spent a lot of money on building a text-to-text model. So you have already, for example, Llama 2 or Llama 3, or you might have GPT-3 or GPT-4. And this model, of course, only handles text, but it has been trained with a lot of knowledge. So you might want to bootstrap that in order to build a model that supports both text and speech. So what you can do, or what you can think of doing, is adding on, at the left-hand side, you can add on a speech-to-text model that will convert from speech to text. And then you can feed the text into this original pre-trained model you have here, like Llama. And then you can take the output text and put it in to a pre-trained text-to-speech model, for example, a Parler model or Mello. These are two we'll talk about later. So this is how you do a modular-based approach for multimodal. You just you cobble together three different models: speech-to-text, text-to-text, and text-to-speech. And this is the way that we're going to look at today using the Hugging Face repo. And you'll find that it works pretty well. Although there is one drawback in terms of power. And the drawback of doing this, let's call it a modular approach, is that there's actually a lot more information contained within speech than there is within text. With text, you simply have words, whereas with speech, I'm not just saying words. I have tone in my voice, I have pace, I have emotion. So you can think of it very simply as words plus kind of emotion, tone, prosody, some of these different words. There's a lot more than just words within speech. So basically, if you take this naive approach here, you're converting rich information, which is speech, into a lot less rich information, which is only text. Then you're going text to text, and you're bringing this text back up to kind of a speech format, but you've lost the richness that was in the original speech over here. So you can do better than this approach of the modular, and you can do better by maintaining that added emotion or prosody, maintaining that extra character that's in speech beyond simply the words. And at a high level, the way you do that is, instead of forcing the model to come down to text and passing text into the transformer, you really want to pass all of the information, so the words and the emotion and the tone. You want to pass everything in the form of vectors from your first, let's call it model, onto the second one. And likewise, you want to pass all of that information, words, tone, etc., onto the last part. And the way you can do this is, instead of using a model that is purely doing speech to text, you use a more general model that's capable of outputting vectors that contain this tone and emotion. And this is called an adapter, which really is another word for just a model. And likewise, on this side, you want to take in the full information, not just the words. You want to take in the full information in vector format so that you can use that in producing the final output speech here. And this is a bit what Llama 3 have done. So you'll be familiar with Llama 3 as a text-only model, and that is true because the speech model, as of making this video, has not yet been released, but it will likely be released at some point. And you can see in the paper already how they have integrated speech. And the way they do it is with this type of adapter approach. So they take speech, they put it through an adapter. So now it's basically represented as vectors that contain information on the words, but also on the tone, etc. And then that's passed into Llama. And then this leaves here as tokens and embeddings. Now, notice in this implementation, we are just coming out with tokens, but we're also coming out with embeddings. And it's the embeddings that can contain more information than the words alone. And this allows you then to improve the prosody, which has to do with the kind of pace and the sound of the speech that is being emitted. So we know what Llama 3 is doing. We don't know exactly what OpenAI is doing because it's a private model, but suffice to say, in a lot of cases, it can be beneficial to bootstrap by using parts of models that you have already spent a lot of money training. And then by applying adapters, you can basically get a boost in starting your training by not starting from scratch with the entire process. So just to recap, in the case of Llama 3 and who knows GPT-4o, you have a more integrated model where the speech comes in. It's going to maintain all of the information in the form of vectors, not just word information, but emotion, tone, prosody. It will go through a transformer that predicts the next token or the next representation in the series. This is also a rich representation, and then this rich representation can be outputted into speech. Now, just to point out, this implementation would still be able to handle text, so you could input text in parallel with the speech right here. There will be an embedding layer that converts this text, these tokens, into vectors as well that are compatible with the vectors that contain more rich information. And likewise here, there will be an embedding reversal where you go from vectors back out to tokens if you just want to produce tokens and not go all the way through to speech. But in this video, I'm going to talk about a simpler approach. It's the HuggingFace approach, where we don't pass rich information through. We only go from speech to text to text, and then text to speech. This means we lose some of the emotion or prosody information that's here. Now, there are ways you can hack this by kind of bypassing some of this. You can bypass and maybe pass in a representation of the emotion to this text-to-speech model here. So there are ways that you can kind of more naively and quite effectively pass information to the output. But in simple terms, it's going to be a modular approach. And the reason why this is much easier is because you don't need to do any training at all. There are no adapters required because you produce text and the model takes in text and outputs text, which is what is necessary for the text-to-speech model. So this simplifies things greatly in terms of having a working model. But as I said, it has the drawback of not being entirely integrated in terms of using the rich information. And the other drawback is that if you put a model together piecemeal like this, often the way that you have loaded all the models onto the GPU, it won't be straightforward to do parallel inference of multiple speech inputs. So if you're trying to run a server that will serve 100 or 1,000 people, this isn't going to be an ideal setup because you're not really inferencing, you're not running all of the matrix multiplications, you're not passing the information in parallel. You're kind of calculating everything here, taking the outputs, taking that batch of output, putting it in here, then doing more calculations, getting some output here, not just one token, usually a series of tokens, taking that batch and putting it in here. And that approach is just not as conducive to parallelization that you need if you want to provide a server for inference at scale. However, it works fine. If you just have one voice input, then this is going to work fine as an approach. So the way that the HuggingFace modules work, there are actually 4 of them. I've shown 3 here, but there's one step that you need before you go to speech to text, and it's called voice activation detection. You need to know when somebody is starting to speak as opposed to just there being noise in the background. So if I leave a pause and then I ask a question, how are you? The model needs to know that I've started to speak, and it also needs to know that I've stopped speaking. So this is an important challenge if you're going to go with the modular approach, and it's addressed in the HuggingFace repo by using a voice activation detection model, which is trained specifically for detecting the start and end of speech. Then there's a speech to text model, text to text, and text to speech. Now, within the speech to text model, you can choose which model you want to use. Obviously, a smaller model is going to be faster, but it will be lower quality. The models here, typically it's common to use a whisper type model. That's an open source model from OpenAI that comes in different sizes, tiny, base, small, medium, and large. There's also a distilled version of some of the large models called Distill Whisper. That's a model that HuggingFace have distilled from large down to the size of effectively a base or a small model, but that performs similarly in terms of word error. And there's also a lightning model, which is a very fast whisper model. I haven't dug in too much to those details, but it's the one that will be running on Mac for the fastest speed. Now for text to text, the options, and you could include any HuggingFace model here. There's small LM, which is only a 360, I think, million parameter model. So very small, very fast, although it gives reasonable answers. It's not going to give very complex reasoning at that size. Llama, 2 billion parameter, Phi3, about 3 to 4 billion parameters. So depending on the RAM that you have, you can use a larger model for higher performance, but it will, of course, be slower if you use a larger model. And last of all, for text-to-speech, the 2 main options I'll look at are Parler and Mello. The main difference between these 2 is that Parler is a transformer model, so it regressively calculates the next part of the sequence. So you put in input text, and it will calculate the first part of speech. It will put that as an input, calculate the next part of speech, the next. So it regressively calculates the next part of the audio, whereas Mello is a once-through approach. It's using a gained adversarial network. If you want to learn more about the different approaches, you can check out my text-to-speech video I made recently. But the benefit of doing a gained adversarial network is that you produce all of the audio output in one go for a given sentence, let's say, and that means that it's faster. So Mello is what we're going to use when we're on Mac because we want speed. I don't have that much RAM. Whereas Parler, it's a transformer approach. It's maybe a little bit better quality, but it is slower. Now for the demo part of the video, I'm going to show you how to run the HuggingFace speech-to-speech model on a Mac. I'll show you some different tips for getting good performance. And then I'm going to run on a rental GPU with RunPod. You can use FastAI as well. And then I'll talk about improving latency. So you can find the full repository from HuggingFace at GitHub. That's at HuggingFace/speech-to-speech. And you'll see all of the instructions here. You can see Andy is doing a lot of work and there are constantly improvements that are being pushed. So you'll want to check this out if you want the latest improvements available. Now, I've written out some notes that will help me guide through the installation. I'll talk through them here so you'll be able to copy them yourself. If you do want just kind of the handiness of having everything in one place, it's here for those who have lifetime access to the advanced transcription repo. This is a private Trellis repo that explains how to fine-tune speech-to-text models and text-to-speech models. And now I just have a README that's going to help me guide through this installation process on the Mac. So I'm going to open up a terminal and let's see, I have one open here. And I'm going to do the installations using UV, which is a Rust package for installing Python packages. And it is really fast and really nice. I recommend trying it out. So the first thing to do is to clone the HuggingFace speech-to-speech repo and then CD into that repository. Now I'm just going to go back. I have cloned it earlier, so actually it looks like I have not cloned it. So let's just do everything from scratch here. I'm going to CD into the speech-to-speech repo. It's cloned. Okay. Now I'm going to fetch. You don't have to fetch if you just cloned. I'm going to activate a virtual environment and I'm going to install the requirements within the HuggingFace speech-to-speech repo. So let's go ahead and do that. And you can see here, if I just do ls, you can see that I have all of the files that are going to be needed, and I have the requirements as well, which are going to be installed here. So git fetch all, pip install requirements. There's also requirements for Mac. That's another option as well. But I know this one works reliably for me, so I'm going to stick with it. The next install is the NLTK library. This is a natural language processing library that's used for tokenizing. And then the next thing that will be cloned is Mello TTS, and that's because I want to run this small text-to-speech model. So I'll require cloning that and then CDing into that repo, installing the requirements. And I do have to install Unidict. This is actually needed for Japanese text, which kind of doesn't make sense because I'm not going to run Japanese now. But to avoid any errors, I'm going to make sure I run that and install the requirements within Mello TTS as well. So I'm going to run all of those. It should take a moment. Pretty quick to clone, but downloading Unidict is like 500. Next, I'm going to install Lightning Whisper. This is a fast whisper model. I'm trying to maximize speed because I'm running on Mac. I have a Mac M1 with 8 gigabytes, which is the smallest possible Mac you could run reasonably on. Ideally, you would have 32 or 64 gigabytes of RAM in order to run this more effectively. So once the requirements are installed and everything is downloaded, in fact, I'm going to CD back into the speech-to-speech folder, and I'm going to just run the requirements installation again. That's to make sure that everything is properly installed, because I've run into errors before when I didn't run that. And only then will I run the Lightning Whisper. So I'm back in the folder now, and I'm running the installation again. Everything looks fine. And next I've got my run command. So let me just copy that into the terminal. We can have a look. So here I'm doing UV run Python. So I'm running speech-to-speech pipeline.py. This is the server command, but I'm going to be running it on my Mac device, which is why I have device MPS. That would be CUDA if you're running on CUDA. And then mode is local, which means that I'm going to run both the server and the client at once within the script. So the server is what runs all of the language models, and the client is what makes requests. So it will take audio from my mic, send it to the server, and get back the response. And then here I'm setting my different models. So speech to text, I'm using Whisper MLX. MLX is a package for Mac that allows you to make use of the GPU if you have an M1, M2, or M3. So it's kind of an alternative to running with Llama CPP. MLX is more Apple native, but this allows for good speed. So I'm using Whisper MLX on the speech to text, and that will default in the back to the Lightning model. For the language model, I'm using MLX LM. I think this defaults to the small LM model right now, but I'm actually explicitly going to pass in the small LM model as the LM model name. So I'm using small LM 360M instruct 8-bit. I'm using an 8-bit model, so that'll hopefully reduce the VRAM, the RAM requirements as well for my Mac. And notice that I've gotten it from MLX community on Hugging Face. They have a repo with MLX quantized models. If you're going to run a model on MLX, you do need to use an MLX model. You can't just use a Hugging Face transformers model or safe tensors. And lastly, I have the text-to-speech model here where I'm choosing Mello. So I'll go ahead and run that. So you'll see Flash Attention is not installed. That's correct, because you can't install Flash Attention on a Mac, as far as I know. This would be used for CUDA. Next, you're seeing the voice activity detection model that's being downloaded. So this is about 1.5 gigabytes in size. And next, the Lightning Whisper model is going to be downloaded and warmed up. And actually, I think what's happening here is we're downloading from MLX the still large V3 model. This is sized about like the base or the small model for Whisper, but has similar quality. And it's actually being inferenced through Lightning. So I think I'm mistaken. Lightning is not a model itself. It's rather a package that allows you to run at higher speed. So after the Lightning model is loaded, next is the language model. So this is where the language model is being loaded here. And last of all, then we are going to load the text-to-speech model. Here you can see the text-to-speech model, and that's Mellow TTS. So everything is being loaded up. And actually, you can see that I've already started to talk to it and it's picking up text. So I'm going to restart that and we'll try again. So once it starts up, I'm going to talk slowly and try to get an answer. Okay, I have my AirPods now, so I don't feed back any sound. The Whisper model is loading, and then the language model is going to load. And last of all, the text-to-speech, the Mellow model. So I'm going to stop talking so that I don't accidentally give input to the microphone, and then I'll ask a request. Tell me a short joke.
Here's a short joke. Why did the chicken cross the playground?
Tell me a funnier one.
Here's a funnier one. Why did the chicken cross the playground? Because it wanted to get to the other side. This joke is cleverly worded, with a surprising twist at the end.
Okay, so that's a quick example. You can see that the Mac is really being pushed. We've loaded in, 4 different models with 8 gigabytes. That's really not a ton, but it is responding reasonably. You can see it's moving through the steps. It wasn't really able to get me a funnier one. That's probably down possibly to the weakness of the language model, the small LM. So if you use a stronger model, like maybe even Llama 2, that would provide for better type responses. Let's quickly try that actually. So I'll just swap in the quantized model here, and it's going to take a second for quantized Llama to download. It's quantized, I think, to 4 bits. I'm not sure if it's MLX. Probably is quantized to 4 bits, and that means it's going to be roughly about 1 gigabyte in size, I think. Tell me a short joke.
Here's a short joke. Why did the chicken cross the playground?
Tell me a funnier joke.
Here's a funnier joke. Why did the chicken cross the playground?
Okay, so running with Llama was not particularly better. It was definitely slower though, a lot slower. And that's just because the memory of my computer, especially recording, is definitely being pushed. But you can see the pipeline is working as you step through it. If you had a stronger Mac, you would be able to get pretty good responses, especially if you can crank up the model size to use a model like Phi, or even Llama is not bad. That wasn't a great example, but in general, I found Llama Instruct, the 2B Llama 2 model is not bad. So that was the demo running on a Mac, and now we're going to run on a rental GPU. Of course, this will provide a lot more VRAM, so we should be able to get quite a bit better performance. Now, again, follow the latest instructions by going to HuggingFace Speech-to-Speech. I'm just going to follow some custom notes that I've written down earlier. for running on a remote rental service. Now, there are two parts when you're going to use a remote service. You're going to set up the server, which is going to have all of the models loaded. And then on the client side, client means your laptop in this case, or my laptop, I'm just going to run a program that will collect chunks of audio, send them to the server, and then receive those chunks back and play them to me. So yeah, there's a server setup and then there's a client setup. Now, the server setup is pretty easy. If you use a one-click template, like I'm going to do here, you can click either of the one-click templates. If you really want to install manually on a GPU, you can do so. I've recommended a base template to use and then the install scripts. You can also just use the direct Docker image that I have built, which can be downloaded from Trellis Research /speech-to-speech-CUDA. It's a fork of the HuggingFace repo. I've just made a few tweaks to the Docker file to add flash attention and to add HF transfer for faster weight download. Okay, so I'm going to click on this one-click run pod template, and I'm going to select the cheapest GPU, or one of the cheapest rather, which is this, it's unavailable. Now, just one tip, which is that latency does matter when you're doing speech. So ideally, you want to pick a GPU that's going to be close to you. So let's see if I can find one. I don't like any of these. Yeah, this one here should work fine. It's in South Europe. I'm in Europe. Well, I'm in Dublin. Be better if I had one in Dublin, but this is fine. So here's the template, and we'll take a quick look at what's happening. It's using the Trellis speech-to-speech Docker image, which I've built using the speech-to-speech CUDA repo here. And a few points. So you need to expose a port for sending and for receiving. So I'm exposing the ports 12345 and 12346 TCP ports. And I'm also specifying a few things here. I'm specifying the model, the language model I want to use. You can specify the speech model or the text-to-speech or the speech-to-text model, but I'm going to go with the defaults. So I'm just specifying the language model to use a small one. I think the default models are going to be parlor, so it'll be a transformer for the text-to-speech. And on the speech-to-text on the front end, that's going to use, I think, the distill whisper model as a default. Here, this is just setting the send host, the host to zeros, and both for the sending and for the receiving ports. And in environment variables, I've set HF hub enable HF transfer. It speeds the weight downloads, and you can optionally set HF home for where you want the weights to be downloaded. Now, there are, I haven't said anything, so I can just click out. There are instructions here in the README. So if you go to this template, you can find all the instructions on how to run the client side, which we're going to follow in a moment. And I should mention that if you want to get the links to these one-click templates, they're also in the one-click LLMs. This is where all of the one-click templates are for all language models. You can just search for HuggingFace Speech-to-Speech. That will lead you to one for RunPod, and there should be another one then for Vast AI, which is just a bit further down the page. So with that, I'm going to deploy the pod, and it should get started here. And in the meantime, I'm going to go back and get my client set up. So for that, actually, I can take a quick look at the README. And here are the different things you're going to need. You're going to need to git clone the speech-to-speech repo, the HuggingFace speech-to-speech repo. And you're going to then need to run some installations. And then you'll run this command, listen and play. And you need to run it with the host of the RunPod server. And that's the server IP address, and then the send port and the receiving port. So I'll show you how to do that in a moment. But first, I'm just going to get a full list of commands for running. So going to speech-to-speech, HuggingFace, GPU installation, client setup. So as I said, I'm going to clone the speech-to-speech repo. It doesn't matter if you clone the Trellis one, which has got the Docker template, or the HuggingFace one originally. I'm going to CD into that, create a virtual environment, install the requirements. Sound device is needed. That's why I typically do apt-get update, because that updates all the packages needed for sound device, and then I'll be able to run here. So let me just copy that and go to my terminal. And within the terminal, I've already cloned earlier the speech-to-speech repo. So what I can do is skip past that step there. And I'm already in the repo as well. I don't need to CD. And I've probably already activated my virtual environment. So I just need to install the requirements and sound device, which should be pretty fast. And now I need to prepare the command that I want to run to hit the server. So once that's installed, looks like maybe it wasn't fully installed, but UV install is very fast. So I've pasted in the command, and this is going to run the listen and play script. But I do need to make a few updates. I need to put in the correct host, and I need to put in the correct ports. So I'm just moving through here to replace the host. And I'm going to get that from RunPod. It's unfortunately not connected just yet, so I'll have to wait a moment until the connect button becomes available. Okay, so my pod has started up, and if you check the logs, you can see that the container has been downloaded and started, and you can see also the Whisper model is being warmed up, the language model is being warmed up, and it's about to start the the text-to-speech model. But in the meantime, we need the correction parameters, so I'll go to the TCP mapping. I'll get the public IP here and go back to my terminal and paste that in here. And now I need to adjust the sending port. Now, we expose the port 12345, which corresponds to, that's the port inside the pod or the instance, but we need to hit the external port that corresponds to it, which is 22062. And we also need to hit the correct receiving port, which will correspond to 12346. And so I'm going to copy that and press enter. So with that, we should be hitting the server. Tell me a short joke. Actually, I notice here a mistake now as to why that wasn't responding. So I'm going to fix this here. Just make sure the host should be matching. So I should see on the connection parameters 24580. And the send port is 062 and 063. So that looks correct. So let's run this, and I'll be silent because then I'm going to give a voice command. Tell me a short joke.
Here's a short joke. Why did the chicken cross the playground? Because it was hungry.
Was it hungry or was it thirsty?
The chicken was hungry.
How do you know the chicken was hungry? It sounds to me like it was thirsty.
That's right. Chicken was thirsty, and it was also hungry.
All right, so that was the demo, and you can see it works pretty well. And that is using pretty small models. So the performance, just because we have much more RAM, is much snappier, and we're getting some pretty reasonable discussion. There's maybe 1 or 2 moments of lag, but nothing like what I was getting on the Mac. I'll just add one comment here, which is this parameter around play steps S. This controls the size of chunks that the text-to-speech model is creating. If you leave this too small, you'll find that there's choppiness in the audio. And so I recommend setting it to about 1.5, and that's the default value if you just start up the one-click template either for RunPod or for Vast AI. Now, just to comment on latency, I already mentioned how it's important to pick a GPU that's close to you. That will reduce the latency. But there's one other method that's commonly used for voice assistants, and that's using UDP ports instead of TCP. TCP means that you have a socket on the server side and the client side. Initially, there's a message that's sent from the server to the client to say, here, I'm going to send you messages. And the client gets this and says, sending back, okay, I hear the messages. And then the server says, okay, great, I'm going to send you the information. So there's this kind of a three-way, three-message communication that establishes the sockets. And TCP gives very secure connections where you know if there's a disconnection pretty easily because of this three-way messaging that confirms and establishes the socket connections between the client and the server. UDP does not give those kind of guarantees, but it also has less latency. You have straight sending of information from the server to the client. And this is faster and has better performance if you're doing things like speech that require a lot of data to be sent. Remember that speech contains more data on a bits per second basis than just sending text. Now, UDP is not supported on RunPod. It is supported on VastAI. It's also supported on other services like Latitude SH. The scripts need to be adapted if you're going to use UDP, and currently the repository only supports TCP, but perhaps there'll be an update in the future. Now, if you do want to learn a bit more about how UDP works and you're a lifetime member of the Advanced Transcription repo, you can take a look in the text-to-speech folder, which contains the fine-tuning scripts for style TTS. I've now added in this Mellow TTS folder here that has scripts for doing TCP inference and UDP inference and instructions on doing all of that. With thanks to Rohan Sharma, who has done a lot of the work here. He provides the instructions on how you can set up a server for going text to speech, both, as I said, in the TCP format and then in the faster UDP format as well. And now just a quick recap on where to find the right resources for doing speech to speech. Your main port of call is the HuggingFace repository. That's github.com/HuggingFace, and then speech to speech. I'll put a link to that down below. It has instructions for running on Mac or running on GPU. The next repo of interest is Trellis Research /one-click LLMs. It's a public repo and it has those one-click links to RunPod or VastAI if you want to start up a CUDA Docker image and then hit that with a client. Note that the instructions on setting up the client are in the READMEs on those one-click templates. Finally, if you want to see my personal notes for setting up these servers and my different tips, you can access by purchasing lifetime access to the Advanced Transcription repo. That's a repo that also has notes on how to fine-tune speech-to-text and text-to-speech models. That's it for this video. Let me know any questions in general about omni or multimodal models below. Cheers, folks.